Okay, so gonna pick up where we left off last time. I'm sort of doing a bit more of a survey introduction, and then we'll end off with some things that hopefully will get you primed and ready for when you guys start back with your real professor. Okay, so one of the things you're going to first be faced with is, hey, I got a bunch of data. How am I going to visualize this? You know, what are the options? And so you have a ton of options. There's actually almost like an infinite number of options, but these are some of the core main, most common. So if we just look around this room right here, right over there we see a map. Right over there, we see some bar charts, see some more maps. Over here's looks like a box and whisker plot. There's a table on that one. There's a map on that one back there. Obviously, this is the GIS lab, so this is a map-heavy data visualization examples, but you guys get the idea. So it's going to depend on what kind of, so again, you guys are learning to crawl before you walk, before you run, before you sprint. So once you gain some facility, you don't need the guidelines. You guys will start to get a handle on how to do this. I'd say one of the most common errors I see with you guys when you start making figures is you're like, bar chart, I guess do a bar chart. Scatter plot, I guess do a scatter plot. And in context where it doesn't make sense. And so there's various tools out there. I'm sure Professor Cafella will share some types of examples of this for you. But basically, it has to do fundamentally with the types of data that we're attempting to interpret or explore. So one of the most common breakdowns is categorical or numerical, or we might say continuous. So categorical would be something that falls into a category. Black hair, blonde hair, red hair, right? So the redness or blackness or blondness is distinct. I can tell that is separate from this other group, but it's not as if blonde is higher or lower than red or black. It's just different. So that would be a categorical variable. Versus a numerical variable, there's some relationship to things. So something is more north, something is a larger amount, that kind of thing. And so there's various decision trees, but as you kind of go down the decision trees, you kind of say, okay, now let's say I have categories. I have hair color. Now, do I have a black and brown hair color? Or do I have black, brown, and green? And black, brown, and green, and purple, and whatever else it might be, right? So that's going to tend to pull you towards different decision points. And again, you guys will go over all that, but that's the first thing is like, what's the nature of my data? What's the organization of my data? I should say, before we continue on, that maps are their own beast. So you guys all need to take 328. At a minimum, we have other more advanced classes, but at a minimum, you guys need to know that. And in that course, they'll go over some of the most basic ideas about effective graphing. Now, we don't, in this class and in other classes, we don't say you don't use a map. If you have that facility, if you're familiar, if it makes sense, by all means go for it. But this class is going to be primarily about non-map data visualization, again, because that's the focus of one specific class. The short version, though, is that when we show these maps, there's some simple rules to make them more interpretable. And the main thing with maps is we're looking for pattern. We're looking for visual pattern. Hey, is there a cluster of things over here? Hey, are the colors hotter over there? Is there an even smushing of the colors? That type of stuff. And so here's an example. So you guys look at this and tell me you interpret for me what's going on. Okay, so like kind of Great Lakesy kind of area, far up north, up there. Okay, cool. Anywhere else? Yeah, sort of like northern New Mexico-y type of areas, that kind of stuff. What do the colors represent on this particular map? What's that? Yeah. So So what is that? So what is that? You guys seen that word before? What's that? Yeah, yeah. So that's dividing our data into different groups, organizing our groups into different bins. And so a decile is where we've broken up our bins up into groups of 10, evenly spaced tens. And so that would be the folks in the highest group. In other words, the people that had the highest rate of cancer. So that doesn't mean that there is an absolute, the number of people, it might mean that, but it means relative, right? Mortality. So it's not just the number of folks, it's the number of folks relative to the population, right? So the black bar, the black color here does not mean no cancer. It doesn't mean that at all. It just says that's the background, that's the quote unquote typical rate. And so what we're looking at here is this is showing us deviations from the norm. It's not just the total number of individuals. Okay, how about this? Interpret what's going on with this for me. Yep, and you see a pattern to that?
I can see the outskirts were more likely to burn. Maybe the city or closer to the temple was protected.
Yeah, so it's actually, so the fire actually started up here. Actually, where am I? Fire started here, I think. And so basically, it went this away. It went towards the lower left side of the screen, and these guys escaped not because they were safe, or whatever, but these guys actually escaped because they were essentially upwind, and these guys were all downwind. And so the fire came and went bam and hit here, and then kind of like a wave splashing on an ocean, boom, one part of the wave, bent up that way, refracted that way, and one part of the wave, bam, went that way. So the fire was actually concentrated right in the most important, historic, oldest part of the island. Okay, so there's a little legend here. It said destroyed buildings. So red is destroyed buildings. So that is helpful. So you don't necessarily need a huge amount of instructions, labels, all that kind of stuff. Okay, so maps, again, they are their own beast, and you guys should take 328 to learn about them. Okay, let's talk about some more common ones that you guys might encounter or use in a more basic data visualization class. So there are many types of graphs. These are just a few, just to sort of get us going. But there's different types of graphs, and they're used for different purposes. So let's talk about a dot plot. A dot plot is essentially taking those observations and plotting each one on top of another, right? So in this case, the morning class, the score had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 people scored an 80, for example. So that's one way of doing it. Now, I could have just done it with a bar, but this is also a way of actually showing there's a different type of a horizontal one. This is a box and whisker plot. Also has some other names. So have you guys seen one of these before? So do you know? So if you guys have seen it before, can you tell me what this is? What we're representing here with this figure?
Minimum on the far left, quarter one,
Yeah.
median, quarter three,
Yep.
and quarter four.
Yep. So we're showing the entire range of the data, but rather than do like that last one, I did a bunch of dots. It's doing that in a more consistent form. And so central tendency is right here, is this middle line. And then yes, it's in quartiles. So one chunk of the data, second, third, fourth. Histogram is maybe one of the first things she might have you guys do. But basically, this is also known as a frequency distribution. So in this case, this is just one of my variables. This is like, height or what have you, right? And so instead of saying how many, like what's the average height, we're showing the whole distribution. So this is, I guess this is not height. This is weight. This is weight of each package. So here's a particular weight, and now this is a bin. So this is a range. So just like we looked at last time when we had the bins of income, we talked about taxes and that stuff. So here's a bin. Now maybe the bin is 5 units, 10 units, 100 units. It could be different size, but the point is a bin. And so I've counted up how many times did I have measurements that were in this bin, and that's what's shown here. Either the absolute number or the relative proportion. Same thing in terms of a histogram. And then the next guy, and the next guy, and the next guy. And so what we see is as we move towards 1,100 grams, we start to see more packages are in this weight. And then once we start to get north of that 1,100, fewer, or it's less common to have packages that are that heavy. And so for many natural populations, we have what's called a so-called normal distribution, which is very few things on the high side, very few things on the low side, and the most common number of things are right in the middle, right? So we call that sometimes called a bell curve. That general shape, that's very common in nature, very common with many, many populations. And a histogram is one way to start to look to say, is our data, and we refer to that, normally distributed? Is this so-called normal data? That doesn't mean like human normal. It means is it distributed like normal? Okay, then a super common graph, which you'll make many of. Another example would be a bar chart or a bar graph. And so in this case, we have some variable here. So now we're not in the histogram land. Histogram was variable and frequency of that variable, or variable and how many times we get that measurement of that variable. Now we're entering these graphs that are relational, okay? So this is factor 1 over here, and this is factor 2 over here. And you might remember from your introductory classes or whatever, sometimes we call this the horizontal axis. More appropriately, we call it the x-axis. And sometimes we call this the vertical axis. More frequently, we call it the y-axis. But we also call the other name for this axis, not y, but f of x. You might remember that. So this is x, and then we're essentially asking, is this variable an f of x, a function of x? And so when we get into hypothesis testing, that's essentially what we're asking. We're asking, hey, as x varies, does that help us understand and predict nature? As x goes up, does that x value tell us something that we can then predict what the y value will be? And so that's why we oftentimes call it f of x. Is this a function of this? And so in this early part of the graph, it kind of looks like that, right? It looks like here that it's this level, and as we go a little bit farther up on x, the y value goes up, or the f of x value goes up. We go a little bit more, it goes up more. We go a little bit more, so it looks like, oh my gosh, pretty good. If we're in this range, it looks like it's not doing that much, right? That here, if we go, here's this level of x right here, and if I add a little more, if I go to this level of x, it drops down, but then the next level is almost exactly the same, right? And it's more or less flat around here. So there's different ways to look at that more precisely, but that's a bar chart or a bar graph. Then we can talk about a scatter plot. So a scatter plot, again, this is going to be an x and a y, or variable 1, variable 2. The last one I should say is, so we call this the x and y, x and f of x. You might also hear this referred to as the independent variable, this guy, and then this guy as the dependent variable. And again, it's the same idea about testing hypotheses. So as this guy varies, does this guy, does this vertical one depend on that variable? And for the scatter plot, each point is an observation. So here's one of my measurements. When my x was this value, my y was this value. Over here, when my x was this value, that time it was this one. In this case, when the x was maybe the same or very close to it, x value, now the y came out this way. That's a scatter plot. A line chart. Now a line chart is, so a classic example is you guys can, interesting, doesn't let me go back. Okay. Well, anyway, a classic one for you guys is to do a bar chart for everything. Do a scatter plot for everything. It lets me do that, Dr. A. Lame. One of the really great things we have are these graphical user interfaces, these great little things I can throw data in and then go, make me this, right? Very dangerous. It almost always makes you do stupid stuff. So don't just go around clicking on things when you start to get to your graphing. Think about it ahead of time. So every time before you make a graph, pull out a little piece of paper, sketch out what you think you want it to look at. Either what you think the data will look like or the layout that you'd like, and then start to work on making a graph. Especially when timelines get tight, you guys start to go, let me do it. And it'll let you do all kinds of stupid stuff, right? It'll take all the money out of your bank account. It'll do all kinds of stuff. Make you vote for a dictator. It's all kinds of crazy. Okay, so this is line chart. So a line chart we use where this shows usually, it's usually a time thing, season, hour, days of the week, month, that kind of stuff. It sometimes is like sort of ramping up of a condition. And so we add, where you could imagine this could be a scatter plot or something, like a dot here, a dot here, a dot here, a dot here. But we add a line when there is this relationship between the thing to the left and the thing to the right. So, think of attention span during my class, right? So the class is going and it's boring, right? And so yeah, I could just put the time, but really it's more like a time series. So line charts or line graphs are best with that sort of temporal signal, or most appropriate with the temporal signal. And the idea is you would visually follow through the day or visually follow through the time period. And then you'll see various types of stacked bar charts. So either horizontally or vertically aligned. And so in this case, the total, let's say this is how many students are in our class or something, right? So this is the total. So the very top or the highest point or the tallest point of the bar chart would be the value, would be the total number of you guys, the proportion, whatever, number. And then inside here, this is some subunit. So maybe this is blonde hair, maybe this is black hair, maybe this is red hair, etc. So at once you both get a sense of what the overall population is like, and you can look at this. Is this mostly light blue and very little dark blue? Are the colors evenly distributed? That kind of stuff. So a stacked bar chart is useful in certain contexts where you're trying to show one thing, but also allow the viewer to see some of the distribution or some of the structure of the population underlying it. Okay, make sense? Questions so far? Okay, so now there's different approaches that we're going to take when we do data visualization. One of the first things you want to say is, hey, how variable is this data that Dr. Kafella gave me, right? Is it pretty homogeneous? Is it pretty much ones and twos and threes, or are some numbers hundreds and thousands, right? So everybody look at me. First thing you're going to do whenever you get a data set, do not start clicking on crap. Look at it. What is it? What are the variables? So this column says m squared. What does that mean? Does that mean square meters? What? So before you do anything, orient yourself to the data and say, hey, this is height in this column, and what are the units? The units are centimeters, okay? And sort of go all the way through. Don't just grab something and start looking at it. So the first thing is for you to orient to the data. The next thing is you want to get a sense of what the data is like. So we usually use what we refer to as summary statistics, basic stuff. What's the biggest number? What's the smallest number? What's the average value? That kind of stuff. And so while you can do that just in a table type form or in a spreadsheet type form, which is one way to do it, that's cool. You can also use graphs to do that same kind of thing. So if we want to first look at the variability of our data set, we can use frequency plots. So that would be that dot plot I showed you. That would be that box and whisker plot I showed you, or a histogram like here on the right. So all of those would give you a sense of what the data is like. Is it normally distributed? Is it over? What's the range over which it's being displayed? All that kind of good stuff. We do a histogram, and we have one type of thing, hair color. So one of our columns, one of our variables. Let's say we could do that on, in one variable. So if it was like this, really super tall, and like that, that's going to say, ooh, the data is very tight. Almost everything is in the middle. Like there's a few guys over here and a few guys over here, but for the most part, everybody's in the middle. Yeah? Versus something like this, which is more normally distributed, or versus something where maybe it's like this, and they're all equally even across the top. So we're just as likely to get a short person as a medium height person as a tall person kind of thing. Okay, cool. So that's looking at variability. The next kind of broad category you guys want to do is to compare groups. So there's various ways to do this, but a bar graph is a nice sort of starter way to look at, let's say, two different things. So I have the score for my morning class, the average grade for my morning class, the average grade for my night class. Are they about the same grade? Let's see. Right? So the height or the length of the bar is going to tell us what's going on, and this works good for This works particularly well for categorical things. You can do it with other things, but really it's best with categories. Okay, and then if we want to see how correlated things are, there's this usually scatter plot is a great start for those. And so we have to have at least two variables to do a scatter plot. We could have more. We could have, and so all the graphs I'm showing you are just what are called two-axis plots or two-dimensional plots. We can also add a third axis, which would be coming out of the screen towards me, and that could add a third thing. So we could have variable 1, variable 2, variable 3, very easy on that. And then once we go past 3 variables, it gets hard. We could add time. So we could add time, which gets a little tricky, but theoretically could. But certainly once you get past 4 dimensions, it's pretty much impossible. Our brains don't work that way. We can't see in more than that space. So we use different types of things called multi-dimensional space or non-dimensional scaling and stuff that's beyond the point of this intro class. But anyway, so correlation is basically scatter plot. If there's a time component, you can do that with a line chart is a good way to look at that. A very common thing you guys will do, and now this is Dr. A talking, so I don't want to get. I'm not gonna. You guys should follow whatever your professor says. So I'm gonna let her give her advice. But here's my thing: for any class that I'm in, if I see a pie chart, you fail. So pie charts suck. So whenever you see pie charts, I want you guys to boo. So if I put up a pie chart, you're going to go. If I say pie chart, you're going to go. That's right. Your energy level is dropping with each boo. Let's try it one more time. Pie chart. Yeah, baby. That's what I'm talking about. Okay, good. Okay. Better than a pie chart would be a donut chart. Although still, and sometimes just for graphical reasons and layout reasons, sure, you might want to use one of those. But for the most part, you shouldn't use those either.
What is the difference? I mean, is there any difference with data lines aside from one having a hole?
How it's calculated, no. How people interpret it, yes. And so the reason why pie charts suck is because of how our brains work. I'll show an example in a little bit. Let's hold that, and when it comes up, I'll show you. So the reason why pie charts should never be used, and the reason why, generally speaking, donut charts shouldn't be used, and the donut chart is this similar thing, it's just got the middle part carved out, is they're difficult for you to read quantitatively. And we'll look at an example in a little bit. But much better in this situation to do, if you're trying to do like the breakdown, hey, how many red-haired, how many purple-haired, etc. A stacked bar chart is much better, or just a simple bar chart with each of those categories laid out on its own. That way, you or anybody can very accurately tell me what the level of each of those categories is. Is that 17? Is that 25? In the pie chart, in the donut chart, it's much harder, but also there's a bigger problem, which we'll get to. Okay, so if you have proportional stuff, should you do a pie chart? No. Pie chart? No. Yeah, thank you. Okay, that's what I'm talking about. All right, good. Okay, so again, there's infinite ways to go. There's all kinds of fun things that we can do, but you guys will be exploring that over the course of the semester. Let me now just talk briefly about when you do a visualization, what I want to have on there. Obviously, the first thing is going to be your data, all the stuff you're putting in, the bar, the scatter, the line, the whatever. Obviously, that's there. You're going to need to decide initially, do I want to put all of my data in there? So every single little data point, is that what I want to do? Or instead, do I want to do some type of summative, some type of a summary statistic, an average? And sometimes you want all the data, the raw data. Sometimes you want the summary, and it's going to depend. Sometimes you might even want to do both of them. So that's going to be the first. So first you're picking, like, what's my data look like? Okay, cool. Got what my data looks like. Okay, so here are my big options for comparing. Okay, then we're going to do a little look at the data. Let me get a little exploration. Okay, now I've decided I'm doing this type of graph. Okay, cool. Now I'm going to figure out, am I going to put the raw data or the summary data? Once that's done and I start to make it, I need to figure out, hey, how am I going to communicate to people what this is? And so when I showed you guys those figures last time, and I was like, what is this? And you're like, I don't know, is it murder? What do you guys call it? Suicided mascots or something? Like, we didn't know what it was, right? So the first thing is we're gonna tell people, or whatever it was. I forget what you guys did, murdered or something. I don't know. Is the labels? We need everything labeled correctly. Label, label, label. So this is going to tell us the variable, what the thing is, height, let's say. And then, usually, in parentheses, the units of that height. So this is height. So I got the big picture. This is how far this person is off the ground. But then, is that in feet? Is that in meters? Is that in kilometers? Whatever. And then, depending on your graph, like initially when you guys first start making graphs, this is going to be it. But once you start to get some more sophisticated stuff, you might also be adding so-called second order information. So that might be a line of best fit or some other thing that's going to do some type of statistics or summary or trend analysis or something of that nature. And so those things are going to, again, start, boom, get the data in there. Okay, cool. Now I want to make sure I have my labels on there. Everything's labeled. Okay, I got all this thing. People can look at this and can see what that is. Maybe I'm going to do some second order trend. And then at that point, I'm going to start looking at it. Hey, can I take away some things? Do I need to put a number on every single tick mark? Could I put a number on every other tick mark? That kind of stuff. And so as you get more sophisticated, you'll be able to get through that faster. Another common thing, since this is data visualization, there are many different ways to do visualization. Again, sometimes depending on the data, maybe it's a map. Sometimes maybe it's a bar chart. Sometimes it might be a table presentation of the data. And so here's, can you guys see this? So here's this guy. So this is, we did some drugs, and we gave some drugs to people. And so if you guys can't read it in the back, it says proportion of patients with resolution of investigator-assessed upper gastrointestinal symptoms at week 26. Okay, so we gave these people some drugs, and we said, hey, did it calm their stomach down, basically, right? Okay, so this is the same data as this. So, which one do you guys like better? When do you think you might use one? What do you guys think about the benefits and trade-offs of these two things? Okay, Thomas likes the table. Why do you like the table?
It's easier for me to read.
I'm used to tables, so I agree.
Okay. So when you say it's easier to read, what do you mean by that?
I can understand the information
It's right there.
with less time.
Okay.
It takes more time to try and figure out the puzzle of that graph.
Okay. Does everybody agree?
Yeah.
I like the
No, that's good. No. Okay, good. So why? Why do you like the why is the graph on the right preferable? It looks aesthetically pleasing. Oh, that's good. It's teal. I like the teal. Okay, so you're clearly going for the Seattle Seahawks. That's good.
I take that though, but I don't think it works that good.
Okay.
I was gonna say I like it because it's more like spaced out. Like the table, it's kind of hard to look at each individual like number set.
Cool. So again, this is starting to get to the point when you start to make some of these more higher end decisions. There's not necessarily a right or wrong answer, right? There's probably a better answer and probably not, but it's not as if there's only one way to do this, right? In general, tables are going to be best when you want to look up a specific value. So if I want to reference something, what is the level that I saw 75% of the people cured of cancer? Like how much of that drug amount, right? Table, like a reference condition, a toxic level that, they killed all the critters, or 50% of all the critters, like stuff like that. Table really good, totally unambiguous. I just glance right there and it gives me the number. Yeah, so again, that's good for reference, especially long-term reference. This is the classic value that everybody adds to get the chemicals to precipitate out of the liquid or whatever the case may be. Graphs, generally speaking, are better for showing the overall pattern within that table. So which of those values were, so one could be 75, one could be 65, one could be 35. And yes, it's true, we can look at it and see this one's bigger, but we usually see the trend pop out faster when it's visually represented, when it's represented as a symbol on a graph. And so if we're trying to show trends or big patterns, the visual display is good. If we're trying to have reference conditions or something people can sort of look up time and time again, a table is going to be faster for those folks. So again, it's not as if one is right and the other one is wrong. It's what is my goal of this? What am I trying to communicate with this, and who's the consumer of this information? So if I have, this is just a little decision tree thing I put together a few years ago. But so if we have independent and dependent variables, again, that's the x and the y, or the x and the f of x kind of stuff. If both are qualitative, tables tend to be better, because it kind of, if things are qualitative and they're not quantitative, that's a bit harder to do on a figure. A lot easier to do in a table. Lot, like, have a column for the red hair, a column for the blue hair, whatever. Yeah, you guys will go over this. I don't need to go over all these things. Okay, you guys get the idea. When you do a table, though, a couple things to remember. First and foremost, if you have a legend on a figure, the legend is at the bottom. On a table, the legend's at the top. But you don't just want to grab your stuff from your Excel spreadsheet and just barf it into the table. You want to think about structure. So maybe highest to lowest, maybe oldest to newest, maybe, whatever it is. But you want to have some sort of logical order so that people can, make sense of that table. Yeah, and these are some other things. Okay, cool. So we saw this before. Here's a visual that's very dense, right? We talked about this is the original French version, but right, we have temperature, we have number of folks, we have direction, how many people died, all that kind of stuff. So this is an example of a figure that's dense but readable. How about this one? What do you guys think? Good, bad, confusing, unconfusing? What do you think?
I kind of don't like it.
It's trying to give you too much all at once in too many different ways.
It are the words like the paragraphs in the beginning overlapping with the graph. It kind of throws off.
Are they? Oh, sorry, what did you say? I didn't hear what you said.
The driving shifts into reverse like up
This
there.
guy?
It kind of like it makes that spike look much more drastic than it might be if you just had the whole graph,
Okay.
but like in a rectangle like normal.
Okay, cool. Other thoughts? Other impressions or thinking on this? So it's okay. It's all good. So this is looking about prices. This is looking about energy prices is what we're looking at here, right? And so this is actually over time. So here, remember that I said the line chart is usually used to show when things are like in sequential order. In this case, they made a line chart, but they added some additional dimensions to it. So we start off here, and as we go through time, like, you know, so things change. So this was trying to be one of those kind of like that Menard graph of still using two-dimensional space, but try to add all kinds of stuff on there. So I think this is a really effective graph. You guys might disagree. This down here is essentially these are sub-stories. So this light gray thing is this same thing repeated and just part of it called out, and then detailing what was going on, you know, in that era, and then what was going on in this era, and then what was going on in this era, and this era, and this era. So, okay, well, how about this? What do you guys think about this one?
I don't like how the colors don't.
Don't like that they don't match?
No, it says yellow and then it's orange.
Oh, I see. Right. What's up with that?
I like it.
You like it? Why do you like it?
It kind of is pretty clear on what it's describing, and it's pretty clear what it's describing.
Okay, cool. So tell me, what is it describing?
It is the amount of fish caught per day, around,
Yeah.
throughout years.
Right. But what's the main takeaway? So that it is true. That is what it is. But what insights can we glean from
The
this?
only thing that I don't like is that it says fish caught per day. I guess you could zoom in if you want, but it's showing like the difference between yellow perch and rainbow smelt.
Okay, good. But Tim, help her out. What's the takeaway?
It's that the amount of yellow perch are decreasing, but the amount of rainbow smelt are increasing.
That's right. So as this guy, so they're rarely both abundant at the same time. Is the story here, right?
Mm-hmm.
There's either a yellow perch era or a rainbow smelt era.
Yes.
Right. So now there's no title here on that, right? There's no legend here on that. You don't even really need a year. If this said 1980, 85, 1990, the what's that?
There kind of is a legend.
There's no written legend.
Does
So-
that count? Does the fish count?
So the fish is a symbol.
But it's kind of clear what it's showing.
Right, I agree. It is clear. And so what I'm saying is you don't always have to write out stuff in words, right? You can use color, you can use shape, you can use various things that it's okay to have a legend. I'm not saying don't have a legend, but you don't always necessarily need the legend.
No, I mean, I know the graph is probably relating to individual fish per day, but it could also be interpreted as pounds.
True, although this is number of fish, but yeah, you're right. It could be,
Nice to maybe add a little.
yep. So maybe number, like pound sign or something like that, yeah.
Or just
Mhm.
like a little
Good.
I like the last graph. I take it back.
Okay. It's all good. Why?
Well,
It's all good.
I like that it's just like highlighting the certain event.
The patterns and stuff. Yeah, totally. Okay, okay, if you like that one. Oh, drum roll. You guys like this? Here's your map. You guys like maps? Here's your colors. Okay, so this is the type of, again, we're not doing maps specifically here, but essentially each county in the U.S. has some value, or well, most do. There's some counties, these like white guys, where there's no data, so those are indicating blank or we didn't take a measurement there. But all the other ones, they have some. You see it, they have some little number value in there. And so the higher the value, it's like a little pyramid, if you will, a little cone on each of those. And so what you can see here, it doesn't even matter what this, it doesn't really matter what this is. This happens to be Native American remains where they were taken from. But the point is, we can just see there's a lot of tall stuff over here, right? There's a lot of tall stuff. And then the color is, are they still away, or are they still not where they were taken from, or have they been returned? So again, very dense. We started to look at this; it's very dense. But even with all that density and with all those numbers, you can imagine this is in a table. This would be pretty hard to read. You could read it, but it would be pretty hard. But here I glance at it; it's pretty obvious. There's this area, right? Sort of Ohio Valley, kind of this chunk of area, Tennessee, that area. A lot of things were taken. The New Mexico area, the Navajo Nation, and that sort of area, a lot of those, and then a lot from Californian tribes. And of course, there are other places here and there, but by and large, this is where that stuff's concentrated. This is where that activity is concentrated. In this case, it was taken remains. Okay, we'll do a couple more. Ready? I don't know. I have a prediction. What do you guys say about this? But there we go. Oh my gosh! How about that one? It's a news story about prisons. So I think this is a great figure. This particular size of this display makes it hard to read. So if you were looking on my nice screen, you could actually burrow down, but it's a little hard to see. But the point I'm just trying to show you guys is here's one level of data here's one type of a figure, type A. Here's type B. Here's type C. So again, very, very data rich. So if you guys had this as a news article, wherever we're reading it, you could easily spend half an hour just staring at the figures and go, hey, I wonder does blah, blah, blah go up in this year? Does blah, blah, blah go down in this year, right? So data dense. How about this? What's going on here? Gesundheit.
How could roads be almost 100% of all land area?
What's this variable? Distance from the nearest road. What's this? Percentage. So what this is saying, if we pick 1,000, like all the land in the lower 48 states that is within 1,000 meters, we call it a kilometer, within a kilometer of a road, within a kilometer, right? Not a kilometer, but a kilometer or less. That is, as of 2003, that was about 80-something odd percent. We have a lot of roads in our country, right? If we go up to something like 5 kilometers or 5 kilometers or less, I should say, that's like almost 100%. Are there some areas, particularly in places like Utah and stuff, that's farther than 5 kilometers? Sure. But that's a very, 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 very rare slice of our country, right? So visualizations like this sometimes are surprising. You're like, that can't be. That says You guys, somebody said that. You guys said, it's like, what's that? Like 80%? That can't be right. Yeah, it is, right? So sometimes data can be really powerful, even if it's not complex, even if it's not one of those big fancy graphs, all this, just sort of boiling stuff down to the simplest core message. Yeah, there's a stacked bar. What's that? Have you guys? Okay, I should probably go a little bit faster. Okay, so stacked bar chart. How about this one? This is from a capstone, one of our previous capstone presentations. What do you think is going on here? What's that? Uh-huh. Uh-huh. So this is how far away we are from the edge of a marine protected area. So that's a park in the ocean, right? A park where we restrict fishing and other activities. Okay, so this is 20 meters. This is 0 meters. So this would be on the edge, like at the exact border of the thing. And we can either start going into the thing or going farther outside the thing. So the MPA, the marine protected area, is the blue stuff. So this is 20 meters in. This one is 40 meters in. This one is 60 meters in, and so on and so forth. Yeah? Everybody with me? This is non-marine protected area. So this is the outside. So this is, we start at the edge, and then we went 20 meters farther into the ocean, and then 40 meters farther, and then, outside, etc. And this, and then, so that's what the X is. And the question is, hey, does it matter if we're inside or outside the marine protected area? Oh, sorry. And then this one is just like everything all together, just an aggregate. If you average everything and don't look at distance. And so the question is, hey, do we see more fish in the protected area where people can't fish, or does it not matter? The fish just kind of swim in and out and do their fishy thing, and they don't care about the border. The last thing, so this axis is the number of fish per transect. So the number, like when these guys went and looked and counted in a standard transect, how many individuals they saw during their inspection. And the last thing is this. So we're going to get to this next in a second. But so this is, okay, so what's this? The top of this bar. This is telling us that that's a mean, that's an average. And then these whisker things, this is one standard error. One standard error up, one standard error down. And that's a measure of variation, variance. That's not variance, it's a measure of variation. Okay, so what this says, and so the rough rule of thumb with a standard error is if we have the same sample size, something tends to be statistically significantly different if those bars don't overlap. So if those bars overlap and we have the same sample size, usually that's going to mean it's not statistically significantly different. So this guy right here, yes, it looks like this. So the orange is a higher average value. Yeah? But because these bars overlap, that's not statistically significant. That's just random. That's because of the few transects we happen to grab. It's not robustly different. So we're saying, yeah, so when we go 20 meters in and 20 meters out, same amount of fish. Same thing, when we go 40 meters out. Yeah, when we go in, we go out, same amount of fish. This one is almost significantly different, but it's not. So this one, again, doesn't matter if we're 60 meters out, but when we're 100 meters out, we get more fish inside the protected area than we do outside. Overall, there's no significant difference because that washes out. Does that make sense? Okay, so we can both have, and so this would be an example of that summary statistic. So this is not the raw data being plotted. This is the summative data. Okay. Now, we've been doing this for a while. Let's take a look at some classic figures. This is from W.E.B. Du Bois in 1900. Okay, so this is talking about making the case for dignity and equity and paying attention to what was going on with the African American community in and around the city of Atlanta. And so, what kind of figure is this? Stacked bar. That's right. And so, so in this case, he has, and so he's looking at the amount of money people have to spend on different things. So the color here is referencing different expenditures. So the black is rent, the purple is food, the pink is clothing. This one is direct taxes, this sort of lightish, grayish, bluish kind of color, the direct tax. And this is the original manuscript from 125 years ago, which is why it looks a little kind of fadey and kind of torn pages and stuff. And then it's sort of everything else. And so in this case, we use this color coding, which really helps us, right? So now we can, not only is it a stacked bar chart, but we can sort of follow the pink. And hey, what about this group? And what about this group? And what about this group? And what, et cetera. And this is household income and stuff. But then also, he's written the number on the bar to make it. So it is possible, theoretically, you can look at this top of this black bar here and estimate that it's 19%. But he's like, don't worry about that. I'm gonna give it to you. So when you see something like this, the value here is representing the top of the bar, but a lot of times it's hard. Oftentimes it's hard to write that at the top, or it's difficult. And so, so a great example makes it very clear. It says that, for example, these folks the poorest folks pay the largest fraction of their income to rent and to food, right? Okay, cool. How about this one? Same thing from the same figure. I mean, excuse me, the same report, same book. Here's the bar chart. I just showed a pie chart. What are you supposed to do? Pie chart. Yeah, that's what I'm talking about. Okay, so you guys. Okay, now he's also, and it's a little faded, so it's a little hard to read, but he's actually written in the percentages here. So let's see. Red. At this point, it doesn't matter what the categories are. Red versus blue. Which one's bigger?
Red.
Sure, right. How about how much bigger is red than blue? You almost all will get it wrong if I ask you. Because our eyeballs are not looking at how this graph was created. So how this graph was created is we have some number. Again, this is a relative thing. This is like the stacked bar chart, right? But here, instead of height away from the axis, here we do how much of a 360 degree circle is it. So 100% would be, the entirety of the thing. And literally what you do is you start here or wherever it is, and you draw all the way around. You technically do it in angles, but in degrees, but we can leave that aside for a second. So okay, whoop, right? And so that's how we do it. Now, when we have 3/4 to 1/4 or something like that, something really, really very, very basic, that's fine. As soon as we go away from the most obvious 50%, 25%, all of you consistently get it wrong. All of you look at this and you estimate this, and I said, hey, what's this number? You will all estimate this number is way smaller than it actually is, and you will all estimate this number is way larger than it. So what do you think this, if I put the thing over here, what would you guess that percentage is? Like how much? How big is that pie wedge?
Like 70%.
The red one, this one.
67%.
It's hard to say. Maybe he didn't use a full circle. He used
Or of that little piece?
The reason we get it wrong is because when I ask you this question, you look at the pie wedge. Yeah? Right? You look at this thing that's red up to here, and red to here. That's not how you draw the graph. Not at all. You draw the graph based on the degrees. So essentially you draw the graph based on this outer edge. And then for visual purposes, we fill that in. And so you, as a pattern-seeking species, you interpret it as the area. And it's not because you're stupid, it's just that's how our brain works. And so as a consequence, we tend to overestimate the big things, and we tend to underestimate the value of the small things. So again, if it's a quarter to 50%, I guess pie chart's okay. But rarely do we have that. This is much more typical the kind of data we have when we try to put in a pie chart, right? So there's some numbers that are a little teeny tiny, some numbers that are really big, and everybody gets it wrong. Everybody either underestimates the value of this variable or overestimates that. So that's why pie charts suck. They mislead us. Not people are actively trying to mislead us, but we ourselves trick ourselves into thinking incorrectly about them. And so that's why the donut chart is an improvement. So the donut does this sort of same thing. We just cut out all this middle. And so it's definitely an improvement because you don't have this big giant pie wedge, but it's still not great. So yeah. And then we have like our old classic things like this. Okay, cool. Make sense? All right. Why don't you guys take a very quick, like 2-3 minute stretch, and I'm going to